All right, sounds like we're on to the next one, Lee, with RADOS multi-object transaction support.
Okay. Yeah. So this is this blueprint is not originally printed by us. It's printed by Sage and Samuel. So this is for multi-object transaction support. So also we think it's potentially very useful in many cases, such as for and if we can implement the multi-object transaction, so we can greatly simplify the design of the client. So in terms of client, I'm seeing the Ceph clients such as the CFS and the RGW. For example, the CFS, they need, if we don't have such multi-object transaction support, they need to maintain their own journal. Yeah, since they are the many operations refer to different multiple objects, and they need to be done in a transaction. For example, for a simple example like the make dir and the create operation. For the create operation, you need to create a new object, and you need to add an entry in the parent inode, right? So this typically refer to the operations on two objects, and this is done must be done automatically. And also some other like the relay or like the move situation. You move some files from one directory to another directory. So this also needs to be done in the transaction and refer to at least two inode object or the operations. And for RGW on the email list and also the Yoheda has reported many the use cases. So we think it's potentially very useful to implement the multiple object transaction. So for the implementation, so here's our algorithm. It's kind of like the two-phase commit protocol. So for the user interface, we allow client to define the foreign subject. You can refer to the blueprint, our blueprint, the description. So the client can define a list of object writer operations on different objects, and the client could specify a master object. The master object will as the coordinator of the transaction. So based on this define, the client could send a group of operations through the MOSDOP to the PG, corresponding to the master object, to the specified master object. So let's say it's the master. So when master receives the MDSOP from client, it will extract the object write operations by PGs and send them to corresponding PGs. So each PG will receive a part of the transaction and only refers to the operations on the object in that PG. So call those PGs, call them slave. So for the third step, the slave receive from master and part of the transaction, and if they will do the check. If there are pending conventional single object transactions going on, and with the operations on the same object, it will wait until the transaction finished. So if there are pending multi-object transactions with the operations on the same object, it just return it again. So here we cannot wait, otherwise may cause deadlock. And say an email I sent to the email list, so we cannot wait. In that case, we must return it again. Otherwise, the slave will construct the transaction in the conventional way. Now return master prepare ACK. So if error occurred, for example, a read then comparison operation failed, the slave will return master error. So if master collect all the prepare ACKs from the slave, then it will send the slaves prepare commit. Otherwise, if master receives error from slave, it will send the rollback to all the slaves, let them cancel the transaction, and will return the client error. So if all the prepare succeed on the slave side, the master will send the slave to prepare commit, and the slave will upon slave receive the prepared commit from master, and they will write their pending transaction into the PG metadata. Yeah, write them aside, not directly on those objects, just write aside into the PG metadata. Then return master prepare commit ACK. So when master collect all prepare commit ACK, that means all slaves has persisted the transaction. Then the master could construct the transaction, including a write to PG metadata to indicate the transaction in committing, and the write operations on its own data object, and construct such object transaction into the object store. Then return client ACK enable client to return from the write operation. Then master will send the slaves commit. When slave receive commit, they will submit their pending transaction to object store from the PG metadata to object store. So after the transaction finished, so it has been written to the ultimate location. Delete the transaction from the PG metadata, return the master commit ACK, which means those transaction has been applied. The master collect all the commit ACK, then return client commit to indicate the transaction has really finished. So enable client to read operations on those objects the transaction referred to, and delete the transaction from the PG metadata. So that's hopefully the whole process. So regarding the error process, let's consider all the possible situations. So for the first situation, if the slave down, then master could be aware of the slave down by the OSD map. Yeah, it will find the OSD map change and find some slave in my transaction has been done. Then the master will start a super peering. So we call it super peering because it's inter PG peering. So in contrast to the traditional, the intra PG peering. So the master will start a super peering to ask the slave the state. After the slave's PG has returned to active and clean by conventional peering, so the master will ask the slave its state and the process according to the following situations. So on the slave side, if no transaction found in slave's PG metadata, there are two possibilities. For the first possibility, if the master itself not in committing state, then master will resend. That means the slave hasn't persisted its transaction at all. So in this case, master will resend the slave the transaction. Let the slave restart from step 3 as described above. So if master is already in committing, that implies the slave actually has finished almost everything. Since it has already removed the transaction from its PG metadata, that means it's almost on the slave side, it almost has done the transaction. After that, the slave is done. It just don't get a chance to send the master the commit ACK message. So in that case, master need to do nothing. Master need to do nothing. And for the second situation, if there is transaction found in slave's PG metadata, then that means slave has finished the persisting of the transaction, but just hasn't commit. In that case, master will instruct the slave to commit. Let the slave restart from step 8 to finish the transaction. So on the other hand, when slave recover from down, if it found the transaction in its PG metadata, it will also start a super peering to ask master state, and the process according to the following different situations. Yeah, kind of tricky. So if master know nothing about the transaction, which implies that master also has just recovered from down. So it just has lost all the in-memory transaction informations. Then slave, if get nothing useful information from master, then slave just do rollback. And if master loses transaction, the master will direct the slave to finish the transaction as described above. So on the other side, if the master down, then slave could be aware of this by OSD map. And also we'll start a super peering to ask the master state after master PG return to active and clean by the master PG peering. And the process according to the following situations. So if master knows nothing about the transaction, imply master has lost all its in-memory transaction information, slave just roll back. And if master in committing, that means master has already persisted this transaction, and also which implies all the slaves has also persisted the transaction. In that case, slave just restart from step 8 to do the final commit from the PG metadata to the ultimate location. So when master recover from down, if it found that there exists transaction in committing, in the object store during the local journal replay. So it will, if it found a pending transaction, then it will also start the super peering to all the slaves after their state. And if no transaction found in slaves PG metadata, which implies that the slave has done everything. Because the master found it in committing, which implies that the master has already sent the transaction to all the slaves, and all the slaves has already persisted the transaction in only in that case the master will be in committing state. So if no transaction found in slaves PG metadata, then slave must have done everything. So in that case, master needs to do nothing. So if transaction also found in slaves PG metadata, just send the slave, let them commit. Oh, yeah, the aggregation is a little bit tricky. So something to discuss. So as we can see, we can introduce a flag to decide whether we need a special prepare committance step, the step 3. So this step is meant to do a fast deadlock and read comparison check. So if this is not desirable, then the step 3 and 6 could be coalesced. Also, the step 5 and 7 could be coalesced. Nevertheless, it has no impact on the error process we discussed above. Another thing to discuss is for step 8, we could make use of the metadata only journal mode. Yeah, we just talked. And to speed up the write from the PG metadata to ultimate location. So that's basically the description. So what's your option? The algorithm is a little bit big.
Oh, I think this would be awesome. I think right now there's nothing between a trivial RADOS application and something as complicated as RADOS GW. Pretty much.
So yeah, thanks.
I think it's super hard to write anything non-trivial against LibRados right now, because you need to build some kind of multi-object commit operation for pretty much anything non-trivial, and everyone has to do it, and it's tedious, and it would be nice if RADOS did it for you.
Yeah, it does take us some time to figure out the implementation.
Oh yeah, it's going to be hard to do. So I had some thoughts the last time I was thinking about this. One of them is that I don't want to do deadlock detection because it's not possible, at least not in a general useful fashion. So
yeah,
I am
suggesting, we don't introduce the individual step to do the deadlock testing. So we just coalesce.
Oh no, that one's also important for that one's also important for making sure the transactions are going to succeed. The only other option is to have some kind of heavy-handed requirement that the operations can't fail. And you could do that two ways: by partitioning the set of available RADOS operations into those that can fail and those that can't, or by just like printing something to the log saying the user did something naughty, which doesn't seem right. But as far as the deadlock part goes, we could allow people to do sort of non-trivial operations as long as we require them to partition their objects into deadlock classes themselves, such that you can't send, basically to do a lock ordering when they specify the object ops. But that's a secondary concern. We can ignore that for now.
Yeah. So for our design now, we leave the client to specify the master object. That means just as Sage mentioned before. So we want to make the object which do the most big things, like the most data written or something. The biggest task, to be the
should be the master.
It be the master, but in that case, we don't have an easy way to avoid the deadlock. Even a simple transaction just refers to two objects. Let us think just two transactions, and they both refer to objects A and B. So if the client specify, the first transaction A as master,
the coordinator could actually do everything up to step 4 without taking any locks.
Yeah, but
in other words, the coordinator could treat itself as a slave and lock and do the prepares on the slaves in order. So my argument is that in a lot of cases, in Rados GW, for example, when you're creating the bucket index and also atomically creating the object, you know the object doesn't exist. You know that because you're generating an increasing sequence number, and it couldn't possibly exist. If it did, there'd have to be a bug. So in that case, it would be nice if there were a way to assure LibRados that there cannot be a conflicting transaction on the second object. That is, it would be nice if you could designate that as a leaf object in the lock dependency graph, with the other object, the bucket index, that is, being the top level object. In which case, the coordinator could choose to do would have to choose to lock the thing at the top of the lock hierarchy first, the bucket index, and then lock the leaf node. And I think we can put that onto the client, because while we'd like to do a lot for them, I don't think we can do this for them. So it would be nice if they had a good way to specify it. Does that make sense?
Yeah.
That is, in that case, you'd say these two things are at the same level of the lock hierarchy because they cannot possibly have conflicting transactions. And that would enable the coordinator to do them both at the same time. But if you had a case where you had objects A and B that genuinely had different requirements, you could specify them in a list that says first lock A, then lock B. Or that is first prepare on A, then prepare on B.
Anyway, if we just wait, or if we just return you again, we give up. Well, it will never introduce deadlock. That's the general way, to handle the deadlock.
I don't know. Like I said, though, it seems like it's not so heavy a requirement that the clients prove that deadlock won't happen. In a lot of use cases and data structures, that'll just work. So. Although I suppose you just never get the rejection message, so maybe it doesn't matter. Yeah. It may not matter. You may be right. Deadlock detection may be sufficient.
Yeah. Again, the process should be sufficient. Yeah. We don't wait. We don't wait. Yeah.
Yeah.
Wait. So So also for the step 8 here we can make use of the metadata only journal mode to speed up the write.
Oh.
That's just little thing.
So do you marked some of these as nearly done or ongoing? Do you have a GitHub account with an outline of the approach you're using?
Sorry?
If you have a GitHub branch, you probably want to point or email to the list with that sooner rather than later.
Mm-hmm.
So that you can get feedback on the approach and the sort of code structures. The super peering part in particular, I'm going to have some opinions on.
Yeah. We really want to seek help from you. Yeah, regarding the implementation. Yeah, we have done part of the implementation. Yeah, and the for the super peering thing, we definitely need your help. Yeah. So the algorithm itself, do you think it's okay?
I think so. I mean, this is what Sage outlined. I guess I haven't thought about it that much since the last CDS. I think we're going to discover some problems with this as we do the implementation and testing, just because that's the nature of the beast. But I think as a first start, this is a natural approach.
Yeah. Also, it's straightforward actually.
Mm-hmm.
Yeah, just for the error process kind of tricky. Yeah, it's kind of we just bring the peering from the intra-page level to the inter-page level, and for regarding the transaction.
Well, to be clear, this super peering won't actually have really much in common at all with regular peering. It'll just be some additional things, some additional messages the primary sends after it's already completed normal peering to kick off the next part of the process. This won't actually be part of peering. It's just going to be, during peering, it will discover some in-progress operations that it now apparently knows about, and then it'll send appropriate messages to the slave primaries to find out what their current status is. But it'll be after peering is completed. It's not going to, for example, block other I/O. That would be bad. It'll block other I/O in that object, of course, but not on all of the objects.
Mm-hmm. Okay.
Anyone else?
So regarding the flag, should we introduce the flag or not? Yeah, we allow the client. We allow the client to choose. Do we need an individual prepare commit step or not?
To be honest, I think that can wait until later in the process. I think for at least some users, they'll want to be able to abort transactions. It's just really useful. So we'll want that option, and later on we can add an optimization. That's what I would do anyway. I would implement the slightly more complicated version and then optimize it later.
Okay.
Because you actually could get an error, and then you'd have to do something with that. So either you have to prove ahead of time that it's not going to happen, or you have to have some strategy for tolerating it.
Yeah. Okay.
All right, have we just about exhausted this one?
Okay, thank you.
All right, thanks, Lee.
Thanks.
All right, so it looks like